Okay, well, good morning. And it's November, so it's like the year's gonna wrap up pretty soon, right? And then and it used to be like you waited till after Thanksgiving before the radios started playing Christmas music and putting up trees and decorations and stuff. But I feel like it's like everything creeps up or something. So anyway, happy November. And let's talk about our midterm. Our midterm exam will be on Monday. And so I've posted this document, midterm topics. Let's see. Okay, so pen and paper exam here in the classroom. It will be designed for 70 minutes. That's the plan. And then I'll give myself, a few minutes to kind of pass out papers and collect. I'll create a seating chart, and I will send one out over the weekend. So, and I guess if you're watching the video, or if any of you here are left-handed and you want a left-handed desk, there's a handful of left-handed desks, not a ton, but just send me a message, and I will try to make sure you are in a left-handed desk. But you might be assigned to a right-handed desk. Okay, you are allowed a sheet of notes, one page of notes, writing on the front and back. It can be typed, it can be handwritten. Please put your name somewhere on the note sheet, and I'm going to ask students to submit the note sheet with the exam. And I'm going to kind of just assume everyone's going to make a note sheet. I think it would be wise to do so, because you'll need to know like some PDFs and stuff. But if for whatever reason someone doesn't make a note sheet, just let me know at the beginning of the exam. I'll make the announcement on the day of the exam as well, just so I know not to expect a note sheet. But I'm assuming students will make a note sheet for their things. Okay, and then definitely you'll need a calculator. So make sure you bring a calculator. Any kind of calculator is fine, just not your phone, just not like an iPad or computer. Okay, all right. So these are the topics. I hope these descriptions make sense. So one, we will do a little bit of Bayesian stuff. Okay, I will provide a small sample of data that come from some kind of specified distribution. The distribution will be exponential, Poisson, binomial, negative binomial, or gamma. So it'll be one of those things. And some of these are discrete, some are continuous, and so you should you'll probably, I think it's wise to include the PDF, I should also say PMF, of these distributions. And then I will ask you, calculate the likelihood, or I guess find the likelihood function for one of the parameters of the provided data. So if it's like exponential, and I say, okay, the values you observe was like 1.5, 2.2, and 2 or something like that. I will ask you like, okay, what is the likelihood function for this set of data? For the function of lambda being the rate parameter. So I think you had a similar problem in homework 1, covering something like that. So you have homework. Homework is due the day before the exam. And the intention is that, like, by doing the homework, it will help you prepare for the exam. I will also provide the conjugate prior distribution and the corresponding PDF for one of the parameters. So, for something like, say, the binomial distribution, the conjugate prior would be the beta distribution, and I would provide the PDF at least of that thing. Okay, and then so using the data and the conjugate prior, you'll figure out the posterior distribution, and that will be, so in the homework or in the notes, we had like the example of the beta binomial. In the homework, you had something, I think it was, oh shoot, I don't remember. Gamma Poisson? Was that the one of the? You had something in the homework, okay? And so it'll be kind of like that, but maybe just for like a different distribution, or basically just kind of be prepared for any one of these ones here, right? So you can go on Wikipedia, look up conjugate priors, and kind of take down your notes and stuff like that, okay? And then I don't frequently do this, but I will have you write just a few lines of code. It'll just be like a very small thing. You can use kind of like one of R's built-in functions to like generate random samples and stuff like that. So you could say, so you'll write a few lines of R code that would perform Monte Carlo estimation. So you'd say like, R, I don't know, R beta or R binom or whatever it is to generate some values to kind of help you estimate some kind of the expected value of some kind of thing. Okay, so that's for Bayesian inference. All right, we have a topic on importance sampling. Okay, so remember, importance sampling is trying to estimate the expected value of some kind of function where it's the function applied to a random variable x. Random variable x has PDF f of x, and we'll say f of x is one of these distributions, uniform, beta, exponential, or gamma. And then, but the problem with importance sampling is that we are not able to generate directly from f of x, or we don't want to generate directly from f of x. We generate from a different distribution g, and so I will provide values, and I will provide random or supposedly random values sampled from a probability distribution g. Probably not truly random. I'll like have them rounded down to maybe 2 or 3 decimal places, just so your calculations won't be too nightmarish. Okay. Okay, so I'll provide kind of a small sample of values, and then you will kind of manually do importance sampling. So you'll have to kind of punch your numbers into the calculator, and you will estimate the expected value of the function using importance sampling. Okay, of course, your estimate will be terrible because it's going to be based on like 4 numbers or 5 numbers. But if you could do it for 4 numbers or 5 numbers, you could also do it for 5,000 numbers, which would give you a better estimate. But just kind of the idea of like actually conducting out importance sampling. So I think if you understand how to do importance sampling, this should be a fairly straightforward and simple problem there. All right, we'll have, there will also be inverse CDF method for the generation of random values. And so here I will provide an arbitrary, either a PDF for a continuous or a PMF for a discrete random variable. And if it's a continuous one, the PDF could be piecewise. And so I think I had an example of this in the notes of like a piecewise PDF. So, just kind of make sure you understand that. So if I provide either the PDF or PMF, you will find the CDF, and then you also need to figure out the inverse CDF. And then I will provide a couple arbitrary values or random values drawn from the uniform distribution, and I will ask you to kind of convert them from uniform to random values of x using inverse CDF method. Okay, and then we'll have a couple questions using convolutions. And so I'll provide a small random sample of values, and these will all kind of be rounded down to maybe 1 or 2 places after the decimal. And then I will ask you to use a convolution to produce values from another distribution. So I might provide like a sequence of random uniform, and I'll say turn this into a binomial, or I'll provide some random normal values, and I'll say make a chi-square distribution or make a t distribution or make something out of that. Okay. One thing that you might have to do is you might have to go from uniform to exponential first. And to go from uniform to exponential, you would use inverse CDF method. That's, in my opinion, not too hard, using like the log and whatnot. But you'll want to make sure you kind of have that relationship either worked out or put on your note sheet there. Okay? And so possible distributions as far as convolution, where you are expected to know how to generate values from a convolution, the binomial, chi-squared, t, gamma, or beta distributions. And I think these are all covered in the notes as well. Okay, and then the last one will be rejection sampling. And I will give you two PDFs, PDF of your target distribution f of x, PDF of some proposal distribution g of x, and you will have to figure out the optimal value m. M is the value that we use to scale g of x so that g of x is greater than or equal to f of x everywhere. And so that might require either some calculus or just maybe some thinking. Maybe you don't have to, like if it was, say, I think in your homework, you had like the sine function or something like that. And, you technically don't have to use calculus. You can just say, okay, well, the maximum of the sine function happens at, pi over 2 or something like that. And that would be fine. But just a little bit of, you'll have to figure out what the optimal value m is. And then I'll provide some random values generated by the proposal distribution. And then I'll also provide some random uniform values. You'll figure out the acceptance ratio and tell me if these proposed values would be accepted or rejected under this scheme. So it's just kind of like, can you do this stuff by hand? So as you work on your homework, you have the advantage of kind of running computer code, but just kind of make sure you yourself also understand the steps. Okay, questions? So that will be that for the midterm exam. So that will be on Monday, and we'll see you then. Okay. All right, let's take a look at today's lecture. All right, so we are talking, so we left off on Monday, we did limiting distributions and stuff like that. So none of this stuff, none of the Markov chain stuff will be on the midterm. That's not one of the topics listed. So today's stuff and Monday's stuff won't be on there. Okay. So on Monday we said a Markov chain is said to be ergodic if we can start the chain at some arbitrary state I, and then if we let this Markov chain run for a long time, then the probability that this Markov chain will be at any of the other states in the system is going to be greater than 0. Okay, so it just as long as it is possible to be at any of the other states, so we don't want this probability to be 0. As long as it is greater than 0, then we'll say it's ergodic. Okay, and this has to be true just for some I guess for all values t greater than some arbitrarily large but finite value t0. So t0 might be like 1 billion, and you might have to say you got to let the Markov chain run for 1 billion steps, but then after that we can kind of say, we expect the probability to be some kind of thing, greater than 0 for everything. All right, and we said for a Markov chain to be ergodic, it must kind of have these two properties, and one was irreducible, and that was kind of the idea that from any one state, you can end up at any of the other states. So you don't want to kind of have this kind of one-way gate where like once you pass through the gate you can't go backwards or something. So we need it to be irreducible, that you can reach every other state from every other state. Even if it like takes like a long meandering route to get there, as long as there's not a zero probability of getting there, we can say it's irreducible. And then it also has to be aperiodic. That is, we can't say that it's, we had the periodic Markov chain where, you could only end up at state, say, number 2 on like the even values, on even stages of time. And kind of one of the simplest ways for a Markov chain to end up being aperiodic is if it is possible to transition from a state back to itself. So if it's possible to remain at the same state, okay, even if it's just one of the states, if it is possible to just remain at that same state in the next step, then it will become aperiodic. So as long as you don't, you have a non-zero probability of ending up back at the same state for at least one of these things. All right, so we have this example where we have 2 states. So this is one of our simplest examples. And this thing is irreducible. It is possible to get from one state to the other state, and all states communicate to each other. And it is also aperiodic because it is possible to go from one state back to itself, and that happens with a non-zero probability. And I have all of the kind of transition probabilities listed on these arrows, and the corresponding transition probability matrix is shown here. And we said, when you have this transition probability matrix, all of the probabilities within a row have to add up to 1. This would be, the top left is the probability of going from state 0 to state 0, and that's 80%. And the probability of going from state 0 to state 1 is 20%. Going from state 1 to state 0 is 60%, and then starting at state 1 and ending at state 1 is 40%. So that would be the kind of transition probability matrix here. Okay, and so all of these things, so P01, so if we look at this top right corner being 0.2, that is that if you are already at state 0, then the probability of kind of transitioning from state 0 to state 1 is 20%. So we can write P01 is the probability that at time n plus 1 you will be at 1, given that at time n you are currently at 0. And therefore, kind of the total probability of, I guess, of being in state 0 and then transitioning to state 1, okay, will be the probability that at time n you are at 0, and then and we will multiply it by the probability of kind of transitioning. So basically, the probability of going from here to here is going to be P0 probability of being at state 0 and transitioning to state, multiplied by the probability of transitioning to state 1. Okay, so this will be kind of like, how much is flowing from 0 to 1, and then kind of the reverse arrow, or the counterpart will be the probability of kind of being at state 1 and then flowing, transitioning to state 0. So if you're already at state 1, the probability of going to state 0 is P10, which we have marked as 60%, and then basically the amount kind of flowing from 1 to 0 will be the probability of being in state 1, and flowing to state 0 will be P1 to P10. And we want to kind of find kind of this equilibrium state, the distribution over 0 and 1, so that kind of we're at equilibrium, meaning the amount flowing from 0 to 1 is going to be the amount flowing from 1 to 0. And that's really, as far as the two-state solution goes, those are kind of the only amount of flow that we need to worry about, because the amount flowing from 0 back to itself and the amount at 1 flowing back to itself is not going to change kind of the amount of the distribution, right? So if you have a certain amount at 0 and some of it's flowing back to itself, it's going to kind of remain at that number. So the only thing that's really kind of going to dynamically change the distribution over 0 and 1 is kind of the amount flowing from 0 to 1 and 1 to 0. So we want to find the numbers pi 0 and pi 1 such that kind of the amount flowing basically from 0 to 1 is equal to the amount flowing from 1 to 0. So so basically we want to figure out the solution for what P0 and P1 is so that we've achieved equilibrium. And so the kind of that solution we will call pi 0 and pi 1. And so we know that the probability of transitioning from 0 to 1 is 20%, and the probability of transitioning from 1 to 0 is 60%, right? So we got 20% and 60%, and we're just trying to figure out what these values pi 0 and pi 1 are. What's the distribution over kind of the states 0 and 1, so that these two things are equal to each other. And because these are the only two states, we know that these two kind of probabilities have to add up to 1. Okay, so if 50% are in state 0, then 50% have to be in state 1. Or if it's 80% in state 0, then 20% has to be in state 1. So kind of just solving for this, if I divide both sides by, say, 0.2, then we would get pi 0 is equal to 3 pi 1. And then if I divide both sides by pi 1, then we would get the ratio between pi 0 and pi 1. Pi 0 is 3 times larger than pi 1. So using that, so if we plug that back into this equation, pi 0 plus pi 1 is equal to 1, what we will get is pi 0 is 0.75 and pi 1 is 0.25. All right, and so that will work out so that we have the two things add up to 1, and then 20% times pi 0 is 0.15, and then 60% of 0.25 is also 0.15. So our equations are satisfied. I guess taking these two equations and these two unknowns, this is the solution that we arrive at. And so what we can see is that if this is my distribution over the states, 0.75 and 0.25 for our the distribution over state 0 and state 1, and I multiply by the transition probability matrix, we will see we end up back at the same values of 0.75 and 0.25. So this kind of illustrates that when you are at this stationary distribution of pi, after applying the transition probability matrix, we end up kind of back at the same distribution over states. So what we have is that if 75% of the let me just draw our two-state diagram here. So at 0, at 1, 20%, 80%, 60%, 40%. Okay, so if we're going to say this is 0.75 and this is 0.25, we can see that how much ends up back at 0.75? Well, 0.75 times 0.8, okay, that's going to be 0.6. So we basically have around 0.6 in total, kind of flowing back to itself. And then out of the 0.75, then the other 15%, 0.15, flows over here, okay? From the 0.25, 60% of the 0.25, so that's 0.15 is flowing from here to here, and then 40% of 0.25, 0.1, kind of flows back to itself, right? So if we see how much ends up back at 0.75, or at state 0, we can see 0.6 flows back in and 0.15 flows in. So we have a total of 0.75, okay? We have 0.15 flowing out, that comes over here, and then combined with this 0.1, we still will have 0.25 here. And so this is just what you get when you multiply your distribution, our station, we would call this our stationary distribution by the transition probability matrix. When you multiply all of this out, we end up back at 0.75, 0.25. So if we start off here and we apply this transition matrix, we end up back where we started. So once we reach this state, then kind of the distribution over the states remains stationary for all kind of future iterations of the Markov chain. All right, so the stationary distribution is this vector pi, so that it has this property that pi times our matrix P is equal to pi. All right, and this, so we have vector times a matrix is equal basically to the vector times 1, and so this is an eigenvector of the matrix P. Normally it's matrix times vector is equal to scalar times vector. We have the order flipped around. It's still an eigenvector, but it's the left eigenvector, which is, but conceptually it's kind of this same idea. Vector times a matrix is equal to a scalar. In this case, the scalar is 1 times the vector, okay? All right, normally we see it like this. Matrix times vector is scalar times a vector, and that's your traditional right eigenvector. But anyway, the relationship between left eigenvector and right eigenvector is that the left eigenvector is equal to the transpose of the right eigenvector of P transpose. So this is what we're trying to solve for. Pi times P is equal to pi. I can transpose this and I get P transpose, pi transpose, and now this is in the form that we're kind of accustomed to as far as eigenvectors go. So we're just going to look for the eigenvector of P transpose, and then we will transpose that, and that will be our solution here. So if here is my my transition probability matrix, and I want to figure out what my left eigenvector is, okay, I will transpose P, and I will get my eigenvectors of this. So the function eigen figures out our right eigenvectors. And then so I will take my first column of values. This is my my first eigenvector, and I will just transpose that, no problem. Okay, and so and what I need to do now is I need to just scale this. So these are normalized. So this squared plus this squared add up to 1. And what we need is we just need to scale the values so that their squares don't add up to 1, but just the values themselves add up to 1. So I'm just going to take this and divide by the sum, by their sum, and we get 0.75, 0.25. We can even see right here, this value is 3 times larger than this value, which is what we figured out. We said the ratio between pi 0 and pi 1 is pi 0 is 3 times larger than pi 1. And we could see that is the case here. It's just these two things don't add up to 1. And to kind of get our stationary distribution, we just have to scale these values so that they add up to 1. Okay, so that's finding our eigenvectors using R to kind of get our stationary distribution. And I think I showed you this illustration, but I like I like it again. So if what did we say? We said 80%. 80%. Can I get that number? Okay, 80% transition from here to here. And we want to say 40%. Oh no, that's the wrong thing to grab. Okay, wait. All right. Okay, there we go. 40%. All right, and so here I can kind of start off with, really big or really small. It doesn't really matter. Okay, so I'm going to start with a big population over here, small population over here, and we will see 20% transitioning from here to here, and then 60% transitioning, and eventually we reach kind of this equilibrium state where the amount flowing from state 0 to state 1 is equal to the amount flowing from state 1 to state 0. Okay. If I kind of shrink this and make this huge, all right, we'll see the same kind of thing here. So the first thing is we got no one in state 0, all right, and then we're going to have 20% flow, or 60% flow from here to here, and then whenever we get over here, we're going to end up with kind of 20% flowing from here to here, and so on and so forth. And then again, we achieve some kind of equilibrium state here. So kind of no matter where you start, we can put everybody, leave this empty, 20% flow from here to here, and then 60%, and then again, reaching this kind of equilibrium state. I think we can shrink this down even. And let's see, now we can kind of, it's 4 out of 7, so approximately something like that. So we have that. Okay. So, let me give you your first view quiz answer. Today's first view quiz answer is the letter B. B as in bear. All right, so what we see is that once we achieve kind of this stationary distribution, okay, when you take the, so you take your current distribution at time n, which we'll call pi n, and you multiply it by the transition matrix, you'll get the probability distribution at the next step, time n plus 1, which we'll call pi n plus 1. And the thing is that if you continue multiplying your current distribution by this transition matrix P, eventually, well, if the Markov chain is ergodic, eventually it will converge to the stationary distribution. So here's our transition matrix. We know that the stationary distribution is this, 0.75, 0.25, right? And what we will see is that kind of no matter where I start, okay, pi to the n as n goes to infinity, so as long as we kind of let it run long enough, it will eventually converge to this stationary distribution. So here, and we saw a little bit of this illustrated with the visualization here, but here I can start off with my entire mass being in state 0 and nothing in state 1, okay? And I will apply the transition probability matrix. So when I multiply this times our probability transition matrix, I will end up with 80% in the next stage, okay? If everything starts off here, right, I will end up with 80% in 0 and 20% in state 1, okay? And then if I start off with 80% here and 20% here, okay, at the next stage, right, then I will end up with 76% in state 0 and 24% at state 1, okay? So again, 0.8, so, you know, how much will we end up here? It'll be 0.8 times 0.8, 0.64, plus 0.2 times 0.6, so that will be 0.76, and then 80% times 0.2 is 16, and 20% times 0.4 is 8%, so 16 plus 8% is 24%. And then if you take that distribution, 0.76, 0.24, and multiply by the transition probability matrix, we get 0.752 and 0.248. And as it continues to run, it's going to get closer and closer and closer to kind of eventually converge. So here I am just kind of doing it manually in R. So I start off with our transition probability matrix. I'm going to start off with this distribution of 1, 0. For a starting distribution, I'm going to multiply it by P. I get 0.8, 0.2, which is what we have here. Multiply it by P again, I get 0.76, 0.24, which is what we have here. Multiply it by again, I get 0.752, 0.248. And if I just let it run over and over and over again, okay, like 1,000 times or whatever, probably doesn't even take 1,000 times to reach this, But after, say, 1,000 times, I reach kind of our stationary distribution of 0.75, 0.25. I can do the same thing again, but this time with kind of an opposite starting distribution. I will start off with no one in state 0 and 100% in state 1. Over here, I apply the transition matrix, and I will end up at 0.6, 0.4. I apply the transition matrix again, and I get 0.72, 0.28. Apply the transition matrix again, and we can see it gets closer and closer to our stationary distribution, and again, just letting it run many times. And again, as far as my for loop goes, I'm just taking my distribution x, multiplying it by the transition probability matrix P, and then just saving that back to x. And I'm just saying do this again and again and again and again. And after applying the transition matrix many times, I end up back at itself, or back at the stationary distribution of 0.75, 0.25. Okay, so that's just, that's not a proof, but it just kind of illustrates that I could start off with kind of either extreme, everybody at state 0 and no one at state 1, or everyone at state 1 and no one at state 0, or really anywhere in between. And after applying the transition probability matrix many times, we end up at the stationary distribution. Some of you took 102A with me, a lot of you, and so I have this, one of your homework assignments was to code Monopoly, and you kind of wrote a whole bunch of you implemented all of the rules, and you said if this, then that, and if you land on the chance card, then you draw a card, and you end up here and here and here. One thing you could have done, instead of writing all of these codes and rules, is you could have figured out the transition matrix showing the probability of going from one space to any other space. So you could have said, okay, if you start off at space 1, go, then the probability that you transition to, say, space 3 would be 1 out of 36, right? Because you need to roll a 2 to go from 1 to 3, right? And then to go from 1 to, say, the chance space, which is, I think, 7 away, you would have 6 out of 36. So you could figure out the transition matrix. You'd have to figure out a few more rules, because technically once you land on the chance space, then you draw from a deck, and then those could also transition you somewhere else on the board. And so, things get a little bit more complicated. But you could write a large transition matrix showing the probability of going from one space to another space. You could even, it would be kind of tough, but you could also even do the transition matrix of, say, going from jail to something else, because if you roll doubles, you get out of jail, and so you have a 1 out of 36 chance of going 2 spaces out of jail, and 1 out of 36 chance of ending up out of these things, and then all of the ones that don't end up in doubles, you remain in jail, and something like that. Well, actually it gets a tiny bit, because on the third roll you end up getting kicked out of jail, but whatever. You could kind of create this large transition matrix. There's 40 spaces on the board, so you'd have to figure out this big 40 by 40 matrix, basically starting at any one of the 40 spaces, and what's the transition probability of ending up at one of the other 40 matrices. And then you could just multiply by this transition probability matrix, after 1,000 or 10,000 types of things, and you could see what's the probability. And I think if these links still work, I haven't actually tested them. They might talk about kind of treating Monopoly as a Markov chain with a transition probability matrix. Okay, so that's the idea of the limiting distribution. So Markov chains have limiting distributions if they're ergodic. So I guess I should say some Markov chains, the ergodic ones, the ones that are irreducible and aperiodic, have a limiting distribution, and that limiting distribution is the stationary distribution. And so that's where we are. But remember, the big picture is we want to be able to generate samples from some random for a random variable, right? We want to generate samples from the distribution for a random variable. And so what we want to do is we want to use Markov chains to generate these random variables. So how can we use this concept of the Markov chain where we say these things have stationary distributions? How can we use that idea to generate random variables, okay? Well, one thing is that, once we know that the Markov chain has kind of converged to its stationary distribution, then the values produced by this Markov chain will come from the stationary distribution. Once we've reached this stationary distribution, then there's a 75% chance that the Markov chain will kind of produce a 0 and a 25% chance that it'll produce a 1. And that, it'll be kind of our stationary distribution. So what we want to do is we want to be able to design a Markov chain, okay? Let's say there is some target probability distribution that we want to generate values from. Can we design a Markov chain so that the stationary distribution of the Markov chain is this desired target distribution? And what do we mean by designing a Markov chain? Well, can we figure out what values should go in our transition probability matrix? Can we figure out some way to put in, so Markov chain is basically defined by its transition probability matrix. Can we figure out what values should go in there so that the stationary distribution of that Markov chain is equal to the desired target distribution? And if we are able to do that, then all we have to do to get values from our desired distribution is to just let the chain run for a really long time, and eventually it will converge to the stationary distribution. And if that stationary distribution is our target distribution, then the values produced by the Markov chain will follow the distribution that we want. Okay, does that kind of make sense, this idea here? We want to design this thing. All right, so the Metropolis algorithm is basically how do we figure out what these transition probability matrices or transition probabilities should be for this Markov chain, okay? And so this will give us kind of the set of rules that we can use so that after figuring out these transition probabilities, the Markov chain's stationary distribution will be equal to our desired distribution. So I'm going to use this kind of silly example, but it's a handy example from the textbook Doing Bayesian Data Analysis. So I think this is linked in the syllabus. It's the book with like little puppies on the cover. All right. All right. And so the idea here is we have this nation that consists of islands on a chain. All right. So I guess kind of like, I don't know, imagine Hawaii being like a nation or something, okay? It was, right? It was the Kingdom of Hawaii before the U.S. colonized it and then absorbed it as one of its states. But okay, and we're going to say there's a politician that travels from island to island, kind of trying to stay in the public eye, and he kind of wants to. His goal is to visit all of the islands proportional to their relative population, so that the most populous island, he will spend the most amount of time there, and then kind of the least populous island, he'll spend the least amount of time there. And for whatever reason, his decision as far as how to travel is going to be he could either stay at the current island, right? Or he could move to the island adjacent to the west, or the island adjacent to the east, okay? And again, this is completely contrived, but just go along with this for now. we're going to say we don't know the total population of the entire island chain, but we are able to kind of figure out what is the population of the current island and what is the population of the adjacent islands. All right, and you can just be like, oh, keep track of your populations, and then you could figure out the whole thing. But we're just going to say at each kind of state, we only know kind of our current population, our current probability, and then the ones of our adjacent things. Okay, so so our diagram. So we've got this. I forget how many. Okay, so we've got these 7 islands. Right, and yeah, so we have island 1 has a, population 1,000, 2,000, 3,000, 4,000, 5,000, 6,000, 7,000. Okay, so island 7 has the most populous, is the most populous island. All right, and so the target distribution that we are going to go for is we want to end up at island 7 most of the time, or I guess most frequently, and island 1 least frequently. And so if you add up, the entire population of the entire nation would be 28,000, and we want to end up, at island 7 with a proportion of 7,000 out of 28,000, or 7/28, 1/4. Island 6 out of 28. Island 5 out of 28, so on and so forth, down to island 1 with a probability of 1 out of 28. That's going to be kind of our target distribution if our island chain had 7 islands, and if these were the populations. Okay, so we're just using these numbers to kind of keep it simple, but you could generalize this to any situation where you have different numbers for each of the populations, and you just calculate these things accordingly. But here we're gonna just say this is the final populations, and this is our target distribution. Okay, and this is going to be our algorithm that we're going to use as far as traveling that our politician will use. Okay, so each morning the politician's going to just flip a fair coin. If the coin lands heads, all right, we're going to propose moving to the island to the west. If the coin lands tails, he's going to propose the island to the east. And so that's going to be proposed, but just because he flipped the coin and it says go to the island to the west, he's not necessarily going to travel to the islands to the west or something like that. Okay, we're going to kind of check the population of the proposed island. Okay, so whatever island gets proposed, we'll check the population of that island, and we will compare it to the island population of our current island. If the island that gets proposed has a larger population, then the politician will travel to the larger island. Okay, he will definitely go to the proposed island. But if the proposed island has a smaller population, then he might go to that smaller island, he might not go to the smaller island. And his rule for deciding whether to go to the smaller island or not is going to be we're going to find this ratio. We're going to do kind of P proposed divided by P current. So if the proposed island is, say, half the size of the current island, he will go there with probability 1/2. If the proposed island is, say, 3/4 the size of the current island, he will go there with probability 3/4. Okay, and so to do that, so let's say the population of the proposed island is 3,000, population of the current island is 4,000, so he will move there with probability 0.75, and to do that, he'll just generate a random uniform value. If that random uniform value is 0.75 or less, he'll go, and if it's higher than 0.75, then he won't go. Okay, and so if he doesn't go to the proposed island, he will just remain at the current island. He will just remain at the current island, right? And this system works in the long run. If this is his rule for deciding whether or not to travel to, neighboring islands, then the probability that that he is on, any particular island will match the relative population of that island. Okay, so again, just to kind of do it a little bit more concretely, we're going to say our nation has 7 islands. These are the populations of the 7 islands, and therefore the target distribution is going to be this. Okay, so we want the target distribution to be this, and we want the stationary distribution of our Markov chain to be exactly equal to this. All right, and again, this is just a simplified example where we have very simple numbers, so everything's kind of easy to work with. But again, you can just kind of, if you replaced any of these numbers with something else, it would also work. Okay, so does this premise kind of make sense as far as what we're trying to achieve? I hope. All right, so let's say we are starting off at island 4. So let's say we're right in the middle. We have our island 4 has population 4,000, okay? So we're gonna ask, what's the probability our politician ends up moving to island 5, okay? Well, if he flips a coin, we'll propose island 5 if that coin lands tails. And so the probability he proposes island 5 in the first place is just 1/2. And then if he proposes island 5, then he's going to move to island 5 with probability 1, because the population of island 5 is 5,000, which is greater than the population of island 4, which is 4,000. So the total probability of moving from island 4 to island 5 is going to be probability 4/5, and that's going to be the probability of proposing island 5 multiplied by the probability of moving to island 5, given that island 5 was proposed, which will just be 0.5 times 1, 0.5. Okay. What about going to island 3? If we start off at island 4, what's the probability we move to island 3? Well, we flip a coin, and if that coin lands heads, then we propose island 3. So, our rule was if it lands heads, we propose the island to the west. If it lands tails, we propose the island to the east. So if he proposes island 3, then the probability that we move to island 3 is going to be 3/4, right? So we look at the population of island 3, which is 3,000. We look at the population of our current island 4, which is 4,000. So the probability that we move to island 3 is 3 out of 4, okay? Or we could just look at the probabilities in our kind of target distribution, which is 3 out of 28 versus 4 out of 28. Again, that will just be 3/4. So island's 3 population relative to island 4 is 3/4. And so the total probability of moving from island 4 to island 3, okay, is first we have to propose it. That happens with probability 0.5. And then after we propose it, what's the probability we actually go to island 3 is 3/4. So the total probability of going from 4 to 3 is going to be 0.375. So we have to first propose it, and then we have to accept it, and that total probability is going to be 3.375. All right, which means we have a probability that we remain at island 4, and this is going to be, what's the probability he stays at island 4, and we're going to stay at island 4 if we propose an island but don't go to that island. So it will be the probability of proposing island 3 but not going to island 3, or proposing island 5 and not going to island 5, right? So the probability of proposing island 3 is 0.5. The probability we don't go to island 3 is 1/4. So that's 0.125. The probability we propose island 5 is 0.5, but in this case, the probability that we don't go to island 5 is 0, because island 5 has a greater population. So anytime we propose island 5, we're 100% going there. So the probability we propose island 5 but don't go there is 0. But the total probability that we start off at island 4 and remain at island 4 is 0.125. Okay, I hope that's all right. And so now I can kind of fill in one row in our transition probability matrix, okay? So I haven't figured out any of these other probabilities just yet, but at least for row number 4, which is where we end up going, if we start off at island 4, we can fill this out, okay? So if we start off at island 4, there's no chance of us ending up at island 1 or island 2 or island 6 or island 7 because those are kind of too far away. So if we start off at island 4, we can either end up at island 3 or island 5, or we can stay on island 4. And this is the probabilities. And you know, as we expect, the entire sum of this row, the sum of this row is 1. Okay. Oh, let me give you your next view quiz answer, which is D. D as in dog is our second view quiz answer. D as in dog. Okay, let's take a look at another island. Okay, so what if we started off at kind of the leftmost island, island 1, okay? What is the probability that we end up going to island 2? All right, so we end up going to island 2 with probability 0.5 because I flip a coin, and if it ends up basically, what did I say, tails, we propose the island to the east, which will be island 2. And if we propose island 2 has a population of 2,000, island 1 has a population of 1,000. Island 2 has a bigger population than island 1, so if we propose island 2, we will definitely go there, and so the probability of going to island 2 from island 1 is going to be 0.5 times 1, or just 0.5, okay? If we flip the coin and it lands heads, we propose the island to the west. There is no island to the west, right? That would be like island 0. Island 0 doesn't exist, so we could treat it as if it were an island with a population of 0. And so the probability of going from state 1 to state 0 doesn't even exist. That's just going to be 0, okay? So if we're at island 1, the probability that we end up going to the west of that, which doesn't exist, is going to just be 0, okay? So probability of proposing is 0.5, probability of going there is 0. And so therefore the probability that we remain at island 1 is going to be 0.5, right? Because that will happen if we propose island 0 and we don't go to island 0. So that's basically just every time I propose island 0, I'm not going to go there. And so if I propose island 0, I'm going to just remain at island 1, which is going to be 0.5. Okay? But if I propose island 2, I'm going to go to island 2. So, so for this row, so filling this in, I get 0.5 of staying at island 1, 0.5 of moving to island 2, and then I can't go anywhere else. So from island 1, I can really only go to island 2. Okay. So we can kind of go through this for the other islands as well. What about starting at island 2? All right. So if we start off at island 2, which has a population 2,000, what's the probability we go to island 3? Well, we will go there with probability 0.5. That's like if I propose island 3, I'm definitely going to go there because it's got the bigger population. So the probability of going there is 0.5. Okay. What's the probability I go to island 1? Well, if I have to propose island 1, which happens with probability 0.5, but how often will I go to island 1? Well, I look at our relative populations. Island 2 has a population of 2,000. Island 1 has a population of only 1,000. So its relative size is 1/2. So that's the probability that we're going to actually move there is going to be 1 out of 2. So first I have to propose it with probability 0.5. And then the probability I actually go there, if I were to propose it, is 0.5. So the total probability of going from island 2 to island 1 is 0.25, which means the probability I remain at island 2 is basically 1 minus the sum of the other ones. But, I could say, what's the probability I propose island 1 and I don't go there? So that's going to be 0.25. What's the probability I go to island 3? I propose island 3, but I don't go there. That's 0. So the probability I remain at island 2 is going to be 0.25. So filling that in, that would be kind of our second row. And I'm going to just kind of jump ahead to say island 7. What if we start off at island 7? The probability I go to island 8, which doesn't exist, is going to be 0. Okay. What's the probability I go to island 6? Okay. Well, first I have to propose it, and then I have to move there. So the probability I propose island 6 is 1/2, and then the probability I move to island 6, given that I proposed it, is going to be 6 out of 7, right? 6/7. So the total probability I go from 7 to 6 is half of that. So 3/7 or 0.4285. And then, so what's the probability I remain at island 7? That's going to be basically 1/2 plus 1/7, or actually 1/14. No, yes, 1/14. Okay, so that's the probability of proposing island 8 and not moving to island 8. So that's 1/2. Okay, I propose island 8 with probability 0.5, but I'll never go to island 8. So if I propose island 8, I'm definitely staying at island 7. But then there's also a probability that I propose island 6, but because island 6 has a lower probability than island 7, I don't necessarily always go there whenever I propose island 6. So if I propose island 6, that happens with probability 1/5, but then the probability I don't actually go there is 1/7. So if I add that in there, the total probability I remain at island 7 is going to be 0.5714. Okay, so kind of filling this in, following the same rules, I could find the probability for our entire matrix, and it looks kind of like this. So, so in fractional form, if I start off at island 2, I have a 1/2 probability of going to island 3, a 1/4 probability of going to island 1, 1/4 probability of remaining at island 2, and then, over here, basically, if I start off at island 7, probability I remain at island 7 is 0.57143. Probability I go down to island 6 is 0.42857, and everything else is kind of filled out. So this is our transition probability matrix. We have 7 states. 7 states, so our transition matrix is going to be 7 by 7. All right. And how do I demonstrate that this indeed has our stationary distribution? So, so I've entered our entire transition probability matrix kind of in fractional form here, right here. And then so earlier I showed that if we want to find the stationary distribution, we can find the left eigenvector of this transition matrix. So first we'll find the right eigenvector of the transpose, P transpose. So I will take our probability matrix, I'll transpose it, and I'll ask for the eigenvector, and I'll take just the first one there. That's our right eigenvector. And then to scale it appropriately so that the sum of these things add up to 1, okay, we're going to do take the transpose of the right eigenvector and just divide by the sum of all of the values there. Okay, and so this is my stationary distribution, and this is, it says the values, in decimal form is 0.0357, 0.0714, so on and so forth. The last one is 0.25, and I can ask, okay, what happens if I take my stationary distribution and I multiply it by our transition probability matrix, and lo and behold, we get the exact same values again, right? So that's to illustrate that once we're at the stationary distribution and you apply that transition probability matrix, you end up with the same values. Your distribution remains the same, or it's stationary. So this this seems to have achieved what we want, okay? We can also just kind of compare, knowing that this is my target distribution, 1 out of 28, 2 out of 28, so on and so forth, to 7 out of 28. We can say this is my target distribution, 1 through 7 divided by 28, expressed in a row. And I can say, all right, is my stationary distribution, are all of those equal to the values in my target distribution? And that comes back true, right? And then we use all equal because that's like approximately true as far as floating point numbers go. But you could go in and you can type in, where's my calculator app? What is 1/28? And 1/28 is indeed 0.03571429. And what is 6/28? That should be this number over here, and indeed 0.2142857. So it looks correct. Okay, so that's good. It's a good sign. Let me just kind of illustrate how if we let the Markov chain work to run for many, many times, what would this look like? Okay, so we could start off. Let's say we start at island 4. And so this will be day 1. So if we start off at island 4, the probability that we are at island 4 is 1, and the probability of being anywhere else is 0. And then I could say, all right, what is the distribution of where the politician could be after 1 day? On the next day, okay? So if we know the politician started on island 4 and we say, all right, let's multiply it by the transition probability matrix, then this is the distribution here. We have a 50% chance of being at island 5, a 3/8 chance of being at island 3, and a 1/8 chance of being at island 4, right? So this is our probability distribution for day 2, okay? And then so for day 3, we could take this distribution, multiply it by the transition probability matrix, okay? And so this is what we end up getting. We could end up back at island 4 if on day 2 we went to island 5, and then day 3 we go back to island 4, okay? We could also end up back at island 4 if we went to island 3 and then back to island 4. And then it's also possible that you started off at island 4 and you end up at island 4, okay? And you spent 3 days in a row at island 4. So after 3 days, this is kind of our probability distribution. All right, we can end up at island 6 on day 3 with probability 0.25. Basically, if we started on Monday, on Tuesday we're at island 5, and then on Wednesday we end up at island 6. So if we propose island 6, kind of twice. And we can also end up at island 2. But what's the probability of that? It's a little bit less. We had to go from island 4 to island 3, and then from island 3 down to island 2. Okay. What's the probability we end up at island 3? Well, there's a couple ways we could end up there, right? We could go from island 4 down to island 3. And then we could stay from island 3 and remain at island 3. Okay. We could have also started at island 4, remained at island 4, and then go from island 4 down to island 3, and so on and so forth. You can kind of ask, what's the probability of all of these things, and this is where we could be on day 3. And then if I apply the transition probability matrix again, this is where I could be after day 4. So after day 4, now it is possible to have ended up at island 7. It's also possible to have ended up at island 1. Okay, and we can kind of just keep applying this transition probability matrix. All I'm doing is I'm just taking our pi sub n, and I'm multiplying it by the transition probability matrix. And I can just kind of keep doing this for days, say 5 through 100 here. Okay, and so here it is after 10 days. This is our distribution. here it is at day 11. So I'm comparing day 10 to day 11. And we can see at this point, things are starting to look, the distribution starting to look, the difference between 10 and 11 gets pretty small. Here we're looking at the difference between day 20 and day 21. Our distribution is, the difference there is even smaller. What's the difference between our distribution on day 20 and day 21? And then, once we're at like 100 days out, okay, we've pretty much reached our stationary distribution. So if on day 1 we start on island 4, after letting this chain run 100 times, what is the probability we're at any one of these particular islands? At this point, we don't really know, but the overall kind of probability, this fits our target distribution of being, probability 1 out of 28 here, 2 out of 28, 3 out of 28, so on and so forth to 7/28 being in island 7 there. Okay, so this is just kind of an illustration of our Markov chain running. And the algorithm that we used here is the Metropolis algorithm, but just applied to this kind of island example. And so next week, next week on Monday you have the midterm exam, but in 1 week on Wednesday, we'll look at kind of generalizing the Metropolis algorithm to things other than just kind of this island discrete case here. Okay, your last view quiz answer for today is the letter A as in apple, and we'll wrap it up here. And good luck as you study for the midterm, and we will see you on Monday.